Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about how we need to construct general solutions for a system of linear equations. The system of linear equations is given in the form of AX is equal to B. Then we can solve this using so-called Gauss-Jordan elimination. And the idea would be to just put this solution to this coefficient matrix A along with the right-hand side part vector B and bring this augmented matrix. So this matrix where we put these two matrices together is called the augmented matrix. And the idea is to bring this augmented matrix into the form where on the left-hand side, I'm going to have the reduced row echelon form of this matrix A. And just after this, I'm going to have the vector D, which is going to be the solution vector. So now it appears everything is not so easy and straightforward because the number of the solutions, depending on the number of the solutions, we're going to construct the solutions for the system of linear equations differently. So it is possible that we're going to have a unique solution. So essentially the system has the unique solution. It is also possible that the system has no solution. But at the same time, it is possible that the system has infinitely many solutions. So when we are going to deal with these two situations, when we need to construct the system with a unique solution or the no solution, everything is more or less straightforward. So whenever we need to deal with this situation, when we need to construct the space of infinitely many solutions and write it down in a compact form, then we need to just figure out a couple of techniques, and we are going to discuss exactly this situation in more details. But before, let's discuss these two situations, the scenarios where we need to construct the space with a unique solution, and we need to consider the system when exactly we have no solution. And is it possible to just understand this from this form of the from the reduced row echelon form of the matrix, essentially? So let's start with this example. So hey, we are given this matrix. So this is already in the form of R. So let me write this. So this is going to be a reduced row echelon form of the matrix. And this part is going to be this vector D, which gives us the solution, right? So in order to get the solution, we need to just write this down, this augmented matrix, in terms of the system of linear equations. One more time. So essentially, this matrix, the RRF, has this 3 by 3 dimension. It means that there are three unknowns. So we have got three unknown variables, which are x1, x2, and x3, and we can find them from this matrix. So essentially, in order to do this, we're going to multiply the first row, so essentially 1, 0, 0, right, to the x1, to the x2, and x3 as a scalar multiplication or as an inner multiplication. If you would just multiply this vector to this vector, what you get is essentially x1. Okay, and this should be equal to the right-hand side part. This should be equal to the 3. And again, so every row of this matrix should be multiplied to the vector with the unknowns, and it should be equalized to the constant here from the right-hand side part corresponding to that particular row. So now if you just go to the second row, it's going to be 0, 1, 0, multiplied again to this vector, what we get is essentially x2, and this should be equal to this 0. So now if you go to the third row, it's going to be 0, 0, 1. If you multiply this to this vector again, it's going to be simply x3, and this should be equal to this constant from the right-hand side part, which is equal to the minus 2. So you see, getting the solution for the system was the unique solution is more or less straightforward. So this right-hand side part vector D is going to tell you what is the solution right immediately. So now let's consider an example with no solution. So this is a typical example with a no solution when in the reduced row echelon form part. So again, we're going to just split this augmented matrix into the reduced row echelon part or the row echelon part, right? So and the solution vector D. And again, you see, so here is this strange situation when you've got just all of the zeros here and you've got one here. In this case, there's no solution. So let me explain you why. So again, if I have this 3 by 3 matrix here, it means that we've got three unknowns which we need to solve. So essentially x1, x2, and x3. And again, please note that this is the reduced row echelon form of some system. Okay, so essentially the system might be in this form or might not be in this form, and we can bring reduce the system into this form. So again, if you multiply the first row to this vector with the three unknowns, what you get is essentially, you can multiply this in this way. So essentially, uh, this row multiplied to this vector. So let me write this 1, 2, 0 times the solution vector x1 or the unknown variables. So it's going to be equal to 1 times this x1 plus 2 times this x2, right? So it's going to be x1 plus 2x2. And this should be equalized to this constant from the corresponding row. It's going to be equal to the minus 3. So now let's just multiply the second row. So if you just get all of the constants from the second row and multiply this as variables, it's going to be 0, 0, 1 times this is x1, x2, and x3. And this should be equal to x3, right? And this is equal to the 2, the constant, which corresponds to the second row. And now let's go to the third row, right? If you multiply these three constants with the three variables, it's going to be simply 0, 0, 0 times to the x1, x2, and x3. And if you multiply these two vectors, it's going to be simply equal to the 0. But at the same time, it should be equal to this one, which corresponds to that row, right? So we've got this contradiction that 0 is equal to the 1, right? Which doesn't, which is not true. So that's why the system of linear equations has no solution. And again, when you have no solution for the system of an equation, when you're going to have all the zeros in the reduced row echelon part and non-zero on the right-hand side part or in the solution vector part. So here are the two scenarios which we considered when we have the unique solution and when we have the no solution. And it's more or less straightforward how to construct those solutions. So now let's deal with the situation when we need to construct the space for the system with infinitely many solutions. So in this case, I've got the system, so which is essentially 3 by 3 matrix. It means that I've got again three variables. So the x vector is going to be written like a x1, x2, and x3. So essentially it's given here, right? So this is the x vector. So this is the coefficient matrix A, and this is equal to the B, okay? So we don't have such a situation as in an example above when you're going to have all of the zeros here and non-zero here, right? So you see, so if everything is 0, then it is 0 here on the right-hand side part vector as well. Okay, so it is not the same scenario as the previous example. But we still need to figure out the solution. So again, so what I want is I would like to put this matrix and the right-hand side part into the augmented matrix. So the augmented matrix was A put together with this B. So let me put the A, it's going to be 3, 1, minus 4, 0, 0, 0, 0, 0, 0. Okay, and it's going to be 2, 0, 0. So in order to bring this to the row echelon form, which is a reduced row echelon form, it is just enough to just make this 3 to be equal to the 1, and we can make this by multiplying the first row to the 1 over 3. So what we will get is it's going to be 1, 1 over 3, minus 4 over 3, 2 over 3, 0, 0, 0, 0, 0, 0, 0, 0. So it's already in the reduced row echelon form, and we can try to figure out the solution here. So you see, so the first non-zero element of a row has been called as a leading one, or sometimes we call it a pivot. Okay, so this is the pivot, and so it fulfills all of the three or four conditions of the reduced row echelon forms. So we've got this one, which is the pivot, and if you go to the column where this pivot is located, there are zeros everywhere else. So now the columns, every column of the reduced row echelon form, corresponds to the variables. So essentially, if your system has three variables, x1, x2, and x3, then the columns of the reduced row echelon form are going to correspond to the x1, x2, and x3 correspondingly. Okay? So, and then the column which has the pivot, okay, which is going to correspond to this variable, is going to be called as the pivot variable. So this variable is called a pivot variable because in that corresponding column, there is a pivot or there is a leading one. And the other two, this column and this column, which doesn't contain the pivot, are going to be called the free columns. Okay, or and correspondingly, they are going to be called the free variables. So what does imply the free variables is that it is possible to just assign any value for these variables x2 and x3 as we wish. So what we're going to do is we would like to write down, hey, x2 is going to be a free variable, so that's why I'm going to just write it down in terms of some parameter t1. Okay, t1 is some parameter. And again, x3, since x3 is the free variable, I am just going to denote this as the t2. Okay, so I've just introduced two parameters. Two parameters. So you will see at the end that it will lead us to the parametric equation of a solution space. Okay, so you see, so in this situation, when you're going to have the number of the equations, which is simply equal to the one, right, is less than the number of the variables, then probably you're going to have infinitely many solutions. But what is essentially is important is that to write down those infinitely many solutions in a compact form. So since the x2 and x3 are the free variables, we have introduced the t1 and t2 into them, and I'm just now going to write down this equation. What does this equation tell you? That, hey, it is going to be 3x1 plus x2 minus 4x3 is equal to the 2. So if you remember, if we denoted x2 was the t1, x3 was the t2, I'm just going to substitute them. It's going to be 3x1 plus t1 minus t2 is equal to the 2. Cool. So what I want is now, I would like to just separate all of this term. So essentially, what I want is, I would like to find x1 from here, first of all. So if you find x1 from here, it is going to be equal to the 2 over 3 minus t1 over 3 plus t2 over 3. At the same time, I figure out that x2 is equal to the t1 and x3 is equal to the t2. So what I want is, so this is going to be the solution space, right? Solution space, which is going to depend on the two parameters. So you probably remember that the object or the space which is going to depend on one parameter is going to be a line. The space which depends on the two parameters is going to be the plane. So essentially, the solution for the system of linear equations is going to be the infinitely many solutions, and all of them are from one plane. So let's find this plane. So in order to do this, what I have to do is I need to just write down the solution vector x, so which is going to be equal to the x1, x2, and x3. And this is going to be equal to 2 over 3 minus t1 over 3 plus t2 over 3, t1 and t2. What I want is I would like to split this vector. So split this vector depending on the free coefficients. So here, for example, 2 over 3 is a free coefficient, depending on the t1, the first parameter, and t2, the second parameter. So let's try to do this together. So here, only the first row has the free parameter or free coefficient. So I'm going to write this down as a 2 over 3, 0, 0. Plus, so which of the rows have the parameter t1? So the first and the second, right? So I'm going to write down the t1 was the minus over 3, t1 here, and 0. Plus, and which of the rows contains the t2? So it's essentially the first row and the last row. It's going to be equal to T2 over 3, 0, and T2. Okay, so this is going to be again our solution space. So what I now want is I would like to take out T1 and T2 from the brackets in order to write down the solution space in an elegant form. It is going to be equal to minus 1 over 3, 1, and 0 multiplied to the T1. Plus, if you take out the T2 out of the vector, it's going to be equal to the 1 over 3, 0, and 1 times to the T2. Okay, so this is going to be the solution, the complete solution for the system of linear equations with infinitely many solutions. So where we have introduced here the two parameters, T1 and T2, right? And by just assigning the different values for the T1 and T2, we're able to generate infinitely many solutions. So this is essentially how we are going to construct the solutions for the three different scenarios. So in our next lecture, in our next video lectures, we are going to discuss about the vector spaces of the matrices. And there we need to again essentially try to construct the solution spaces. So thank you very much. Hopefully this video lecture was helpful for you.